Welcome back to another lecture in space robotics. Today we're going to cover the electrical power subsystem. By the end, I hope that you'll be able to define the function, typical requirements, design consideration, and verification methods, and survey various technologies associated with the electrical power system. Let's get into what the electrical power system is. The EPS exists to generate, store, and distribute power to the rest of the spacecraft. Power flows from a generation source through conversion and storage into the management and distribution unit, which delivers power to all loads like the mobility system, thermal control, communications, and science instruments. The biggest power draws on a planetary robot are usually the payload, mobility, thermal regulation, and data transmission. Some space robots also have energy storage. Power generation for planetary robots happens either in situ, using the local environment like sunlight, or from onboard resources that we bring from Earth. On the left, you see a solar-powered Mars rover using germanium solar arrays, which are more efficient than traditional silicon ones on Earth. These arrays can produce up to 140 watts per hour and kept this rover active for over 12 years on Mars. On the right is Curiosity, which doesn't rely on sunlight at all. Instead, it uses an MMRTG, a radioisotope thermoelectric generator that converts heat from decaying plutonium into electricity. Curiosity has been operational for 12 years already, and its mission has been extended indefinitely, but is expected to last 14 years. Choosing between these options depends on mission length, surface conditions, and how much sunlight or dust you expect. The second function of the EPS is storage, holding excess power for use later, especially when generation isn't possible. One example is Mascot, the lander deployed by Hayabusa 2, which used a primary battery, over here, which was non-rechargeable because its mission was short and power critical. Once the battery ran out, that was it. On the other hand, the Artemis CubeSat kit uses lithium-ion secondary batteries, which are rechargeable and paired up with solar panels. This setup is ideal for long-duration missions, where energy needs to be cycled across day and night or eclipse periods. So even within battery-based systems or energy storage systems, strategies vary based on mission length, solar access, and energy demands. Another role of EPS is distribution, or more specifically, regulation, conversion, and isolation of certain power. This is a system architecture diagram from LADEE, a lunar orbiter, which you can see up here. You can see how the electrical power system, outlined in indigo, is deeply interconnected with every other subsystem, from propulsion and comms to science payloads and thermal control. Components like Satori manage operations for spacecraft and payload power, while SASE, I don't know how it's said, regulates input from the solar arrays and handles battery charging. The EPS doesn't just route power, it regulates voltage, converts formats, and isolates faults to protect mission-critical systems. If the power distribution isn't designed carefully, a failure in one part of LADEE could ripple across the entire spacecraft. That's why distribution is just as critical as generation or storage. Beyond generating and storing power, the electrical power system must also survive the harsh environmental conditions of planetary surfaces, just like any other subsystem that we're going to talk about. Take Ingenuity, NASA's Mars helicopter, as an example. It operates in an environment where temperatures can plummet to -107 degrees Celsius at night. Ingenuity's power system relies on these Sony US18650 VTC4 lithium-ion cells, kind of like AA's, which have specific temperature constraints of charging between 0 to 50 degrees Celsius and discharging in between -20 to 75 degrees Celsius. Storage must be kept between -20 and 45 degrees C. And to protect these batteries, Ingenuity employs the Helicopter Warm Electronics Box, or HWEB. This insulated enclosure, equipped with heaters, maintains the battery and avionics within operational temperatures during the frigid Martian nights. Without such thermal management, the batteries could suffer irreversible damage, jeopardizing the mission's success. You may wonder how the electrical power system is able to achieve all of these functions through the technologies available today. There are three major technologies used for power generation in space systems, each suited to a different mission need. On the left, we're revisiting Mascot, the lander that Hayabusa deployed. It used a primary lithium battery, a simple high-energy solution ideal for short-duration missions with no opportunity to recharge. Mascot operated for about 16 hours, enough to complete 2 rotations of its target asteroid Ryugu. In the center, Juno showcases the power of photovoltaic arrays, or solar cells. Its fixed solar panels work even at great distances from the sun, though they had to be especially large and efficient due to the weak solar irradiance at Jupiter. On the right, we're revisiting Curiosity, which emphasizes the thermoelectric RTG, converting heat from decaying plutonium into electricity. This method is ideal for long missions in dusty or sunlight-limited environments, like the Martian surface. So depending on your mission's duration, exposure to sunlight, and operational constraints, one of these power system types may be more suitable than others. When it comes to technologies and energy storage, a good way to think about selection in space missions is a trade-off in the metrics of energy density on the vertical axis and power density on the x-axis. Energy density is how much total energy the system can store in watt-hours per kilogram. Power density, on the other hand, is how quickly that energy can be delivered for peak power. For example, fuel cells and lithium batteries store a lot of energy, making them ideal for long missions, but they deliver power more slowly. On the other hand, capacitors, especially ultracapacitors, can discharge energy very quickly but don't hold much total energy. The curved diagonal lines represent discharge time, so technologies farther up to the right are high performance in both energy and power. But as you can see, no single device does it all. Let's look at how different storage technologies map to real space missions. In the top left is the Space Shuttle. Space Shuttle used fuel cells, which are ideal for human missions needing high energy over many hours, with water as a useful byproduct. I couldn't find any space robotic missions that have flown fuel cell technology, so I had to use this particular example. On the right, Ingenuity uses secondary lithium-ion batteries, housed inside the H-Web. These are rechargeable and paired with a solar panel, but require careful thermal management to survive cold Martian nights. At the bottom is a very unique spacecraft from 2011 called ChipSat. ChipSat used capacitors for storage, offering low mass and ultra-fast power delivery. These are well suited for small spacecraft, about the size of your palm, with lightweight, short lifetime missions. Each of these systems shows how mission context drives storage choice, whether you need longevity, rechargeability, or speed. When designing electrical power systems, one of the first things to consider is mission duration. It directly informs your choice of energy storage and generation strategy. On the left, Mascot used a primary battery. It was a short-lived mission, just 16 hours, so a simple high-energy capacity battery was perfect for powering the lander without the need for a recharge. In the middle, Ingenuity also used a lithium-ion battery, but a secondary type. These are rechargeable via a small solar panel and must survive hundreds of flights and nights, requiring good energy density, long cycle life, and thermal protection. And at the bottom, ChipSat used ultracapacitors. These missions are ultra-short and lightweight, capable of fast charging and high burst power, but with very limited total energy. So whether your spacecraft is operating for minutes, hours, or months, your power system design will look drastically different. Also worth considering when designing electrical power systems is that the environment plays a critical role in system reliability and longevity. In the top left, you see the InSight lander in 2 different time snapshots. One where the solar panels are dust-free, and then in another, the solar panels are covered in dust, so much so that the mission had to be stopped. Dust doesn't just block light, it can also cause electrical shorts and thermal issues. On the right, we see how radiation exposure degrades lithium-ion batteries. Even at moderate doses, batteries suffer significant capacity loss, up to 27% at 9.8 megarads. This limits available energy and can shorten mission life. Below that, the temperature plot shows how battery cycle life drops sharply outside the optimal charging range around 25 degrees Celsius. Higher charge rates, such as 2C or 3C, also accelerate degradation further. Together, these factors of dust, radiation, and temperature demand careful electrical power system design, from shielding and thermal control to component selection and redundancy. Another design consideration is mobility, both orbital and surface. That has a big impact on power strategy. For orbiting systems like the International Space Station, solar arrays are articulated on two axes to continuously track the sun. This maximizes power no matter the orbital position. On planetary surfaces, mobility introduces even more variation. Ingenuity, for example, uses fixed solar panels sized just enough for a short flight per day mission, optimized for mass and recharge rate. Spirit, shown here in winter on Mars, had to park on a north-facing slope to tilt its panels toward the low winter sun, a passive way to increase solar input without mechanical articulation. In contrast, mobility-agnostic solutions like the MMRTG, used on Curiosity and Perseverance, generate power continuously, regardless of sunlight, slope, or dust. These systems are ideal for dusty, high-latitude, or long-duration missions. So the more mobile your mission or the more variable the terrain, the more adaptive or autonomous your electrical power system needs to be. In the next handful of slides, I'm going to go through the process of how to design a power generation, energy storage, and power distribution solution given some design drivers, such as power consumption of other subsystem components, anticipated power possible given the environment, and your concept of operations. I'm going to use this template for a design class I taught and a satellite I designed at University of Hawaii as a case study, which generated all of the numbers and descriptors you see here. You'll have to do this for your assignment, so take note of the process. Our design process begins by understanding how much power each component consumes. This table breaks down the power budget by different subsystems and also by different components. This table should be as comprehensive as possible for all of the power-consuming or generating components in your space robot, as far as you know in your design process. Take note of the percent of the total power budget. For instance, in this satellite, the BeagleBone Black and PiQ boards together dominate the demand in the onboard computer system. If you're working from a template, always update datasheet references and verify that the component list reflects the latest design. This becomes the foundation for everything else downstream, such as power generation, storage, and even thermal sizing. Next, we define when each component is active. This is critical because not everything is on at all times. If we were to be even more nuanced in this table, we could also indicate when components are on but idle, instead of just on and active. For example, our sample satellite has a camera that is only on during data collect, while the transmitter is only on during data transmit. These operational modes reflect the concept of operations, so align this table with your timeline of mission phases or events. Double check that components with high average power use are only on when needed. This is where power saving strategies begin. Now that we know when each component is on, we can calculate power per mode by multiplying power draw from the data sheets with the on-off binary state of 0 or 1. At the bottom, you'll find the average power draw per mode. For example, data collect is the most demanding in this case. Watch for non-obvious peaks like thermal emergency, where heaters suddenly drive up power needs. These values become your design envelope for generation and storage. Once you have the previous table generated, you need to identify which mode draws the most power overall. In this mission, it's thermal emergency, slightly higher than data collect due to the heater load. The highest value here determines your peak power requirement, and you'll size your generation system to meet or exceed this. You may also decide to shed loads or modify behaviors during this mode to bring the power draw down to a more reasonable level for your power generation system. With our peak and average demands known, now we evaluate technologies that can meet those demands. This is a decision matrix with common criteria. such as energy density, mass, thermal radiation resistance, mobility constraints, and more. You can use a subset or all of these different criteria to compare options like solar panels, fixed or articulated, RTGs, batteries, and supercapacitors. Or if you want to go with a specific type of technology, compare against specific manufacturing models across various vendors. In a decision matrix, you can highlight or weight highly which criteria are most important for your mission. For example, you can stress rechargeability for long duration with a high weight, or radiation resistance for outer planets. You can fill this in with either qualitative values, such as high-low, or quantitative scores, and apply weights to choose the best fit. Now that we know all of our components and power demands, we can size and configure the power distribution architecture. Everything highlighted in red here is the electrical power system. It includes the solar input, battery storage, regulation and switching, and monitoring. This layout ensures that we provide the right voltages and current capacity to each subsystem. You'll notice that we branch from VBAT to multiple voltage regulators, such as 3.3 volts, 5 volts, and even 12 volts for different components. Switching is handling via EPS PDU, or power distribution unit switches, giving us mode-based control over which rails are live. This supports emergency scenarios, thermal constraints, or power-saving states. It's important to validate that each regulator can support the peak current drawn during your most power-hungry mode, which we identified in a previous step. Now, in the design process, we have to simulate how much power can be generated over time based on our environment. This example uses STK's solar panel tool, which accounts for orbital path, eclipse conditions, and panel articulation. This spreadsheet output is power in watts per minute on each row. This gets fed into your time-varying power profile spreadsheet. Use this to assess if you're generating enough power to charge batteries or to run operations directly. If you don't have SDK, you can also use AI Solutions Free Flyer software, which has a free educational license. And if you don't want to go as fancy as a simulation to generate a power time series like this, you can look up solar irradiance where your robot is going to be in the solar system to get that total power possible. Then you can apply some efficiency factor from your solar panel spec sheet to get estimated power generated, and assume full power during daylight, times of illumination, and no power during eclipse. Finally, we simulate real-time power balance. Power generated minus power consumed is equal to some power balance. Here is a table that shows the concept of operation or modes over time, over each minute, with their associated power consumption, generation, and battery charge. On the upper left is a plot of power consumed and generated on the y-axis, with time on the x-axis, which visualizes the variance of power across different modes over time. If you don't have an energy storage solution, then you want to make sure that your power balance is always greater than 0, because you can't use more power than you can generate. If you do have an energy storage solution, you can draw some power from the battery to augment the power generation solution. You also want to keep track of the energy storage capacity over time. Here in this table, it is the battery charge on the far right, which shows whether the system charges the battery, discharges it, or runs at equilibrium. Keep an eye out on the battery charge column. If it drops to 0, your design did not close, and you need to revisit your power generation and energy storage solutions, or reduce the power draw from other components, or change your concept of operations. Moving forward, if you wanted to make your design more robust, you could include conversion, efficiency, margins, eclipse buffers to generate more than enough power in case of unforeseen power losses. The final step in power system design is verification and testing. At the top left, we see engineers at NASA Goddard performing electrical integration testing, checking that the EPS interfaces correctly with avionics. This includes continuity checks, voltage verification, and watching system behavior during startup. Below that, we have an example of battery testing in a thermal vacuum chamber. Batteries must be qualified for temperature extremes and vibration. We also run power cycling tests to simulate degradation over mission life. On the right is a plot from an orbital eclipse simulation showing energy use and solar charging during an orbit. Tools like Manage, which is cited in that paper, uses these profiles to guide onboard decisions like delaying sensing operations until there's enough energy available. All of these tests ensure that your system will perform as expected when exposed to real-world stresses, whether in orbit or on a planetary surface. So hopefully, at the end of this lecture, you feel prepared to define the function, typical requirements, design consideration, and verification methods for the electrical power system, as well as the ability to survey various technologies associated with the EPS subsystem. See you in the next one.